All right, we're on the air.
Yeah, we're on air. Hi, everybody.
Hello.
Hopefully you can hear us.
Chat us if you can't. Live and recording. All right. So I guess we had a couple questions to start, or do we want to start with?
I'm just not sure.
I think we're on. If you know us and have our phone numbers, text us that you can hear us.
Yes, we got it. Yes, thank you.
Awesome.
Thank you, Bridget. You're the best. All right, now we're really live.
We're here. Yes.
So I'm Zee. This is Raphael. We're the creators of Root, and we're excited to be here with you guys and show you all about our robots today. There's a Q&A function. Make sure to add your questions or post them in the chat window as things come up. But so far, our two Q&As I will share are Zach asked, can you highlight some of the ways in which Root is interactive and good for groups of 2 to 3? So starting off with just robots and why they're just naturally more awesome than any way that you could possibly learn to code is that you have lots of different responsibilities and jobs, and coding with robots brings those to life. So with our app, you have people that are the drivers and the creators of coding, but then they also have interplay with when the code is operating on whiteboards, how you debug those in real time together. So it's always like a pairs coding kind of thing, because coding with robots, oh, there we go, is special that way. So let's talk about some of the interactive things we do with kids. We're going to start off with what we call the Sidewalk Activity. Is that a good one?
Yeah, so this is also a good example to kind of answer that one question of like, how do kids work together? And we found this is a really good introduction if you've never used the robot. So obviously many of you watching now have not. And we call this Sidewalk. And the idea here is that you create a little game board. So we've got this root on the board. Obviously that has the magnets so it can stick to the board. We can just draw a box around it. And so this is kind of the starting area. But then we can have either you as a parent, as a teacher, or other kids ultimately can create a challenge. The nice part about the whiteboard is you can easily debug if you did a bad job drawing your squares, but this will be good enough.
This is Root 0.
Just connect, it'll light up in blue. So just hit it until, there you go. All right, so we're just gonna start with a simple example here. I drew a little L, so he'll have to know how to turn. And then this is like home. So this is where Root is trying to get to. Nice little windows, some smoke, some winter.
So in a pairs coding activity, you'd start with an app with a blank screen, and kids just naturally understand, this is a touch interface, and they click and drag, and everything is a touchable interface. So when kids touch these sequences, now they see something familiar. They see the game board activity, just like we drew, and they understand that what 0 steps means by touching it, or going backwards 20, or going forwards 20. So kids spend time working in pairs trying to come up with their first coding lesson here, and they would come up with commands like go forward 20, go forward 20, and then we're going to turn. And this is also a touchable interface, so you can understand angles.
So something, that we're not mentioning here is actually that you don't even have to know how to read to use this coding interface. It's all pictures, right? We purposefully didn't show the numbers of the angles that you're turning. It's just, you have a picture of the robot and kind of an arrow of how much it turns, and it will turn that amount. And so you don't have to know angles or some of these more advanced mathematical concepts to get started with your coding.
So there's two ways to run with Root. So you can either hit the play button, and it's going to say if play and execute all of these commands. Or what's fun for kids is they can also step through their commands. So if we hit the step button, it does one sequence. We see it's lit up. We see where we are in the code, and it is 20.
You can even change it. Why don't you add like a light up or something?
Okay. So now maybe over here we want to light up. We'll make the light turn blue. And then if I hit step, so now the light turned blue. And as we continue through the code, we can step through. I went up another 20. Up, I made a bug. I went up too many times. And this is where where coding is really cool with kids, because they can debug together. They can figure out where their mistake was. They can put it back.
So I as the other kid, kind of my job can be managing the robot, creating the challenge or whatever. So I reset it, and if you were to stop this program,
and now we take my my mistake, we drag it to the trash can, and it does a little flushing sound. And now we're back to where we were, and we can step through our code, and it will go up 20.
You can even just push play from here, and it'll run each sequence.
And then we turn left. So this is the beginning fundamentals of what's important in coding and sequencing. So if we look at what we just did here, and we made it turn blue, what happens if we want to start doing more complex things, like maybe we'll make 2 music notes here and here.
I'm actually going to do the same one. So we're going to have Zee introduce kind of another concept. Well, we can start with the long way, or whatever you feel like.
Right.
So now, when it starts, before it starts moving, I want it to play 2 notes on either the iPad or the robot. We'll do it on the iPad, so it's a little louder.
So here we have our interface again, and we're editing our code to go to our piano note player, and we can add a music note C, a music note D, and we can, after the blue light and it goes up 420, before we turn, we're going to play those 2 same music notes, C and D. So here we are developing and modifying a sequence and understanding where are those operations. And now if we hit play, we complete our sequence. So this is very much like a code.org activity. But what's really cool about this stage is kids that understand these tools, they end up making their own sidewalks and their own board games, and they start challenging each other. So now when you have groups of 2 to 3 kids with more groups of 2 to 3 kids, you can have group-on-group challenges where you make a game board that the other people have to do, the other people make a game board that the other groups have to do, and it gets really intense because kids love competition.
They make very cruel challenges, let's put it that way.
and when the challenges start getting cruel, you now try to get into code efficiency. And I'll explain to you what we mean by code efficiency. So there's this boomerang function here. And as we all know, if you throw a boomerang, what happens? It comes back to me, right? Well, at least in cartoons. So just like that, if you throw a boomerang, in this case, it's a purple boomerang, we add a function that says, if purple boomerang, we're going to move our C and D there, and we're going to get rid of the C and D here, and we're going to add another boomerang function right there. So this is exactly the same code, but now we're using efficiency. So now we're actually, if we had to add another block that was C and D, well, that's just another boomerang, no big deal.
Or just as an example, so here we can change the output to play on the iPad speaker instead. And what you do is, because now it's in this boomerang function, if Zee were to make that change, it would happen both times that it plays it. And so you could kind of like update the code in multiple places at the same time, but in a kind of natural and fun and intuitive way.
So I'll just switch to ground mode here so you can see the robot. And I just wanted to also show what we mean by real-time interactive environment. So if we actually get rid of the if, here, why don't you...
Here, I can code it, or you want me to hold it?
Yeah, you hold it.
All right.
So if I got rid of the if by dragging it here, deleting everything. And now we're just going to make a program that says, if I hit play, go to a purple boomerang, and if I'm a purple boomerang, run this function. But now you can call a function on itself. And what you usually would see is now you're creating a function into a loop. It's now stuck playing music notes C and D, and it's real time. if I add a note here and change it, the robot is playing those notes. This has not been done before. So this is what we mean by real-time coding environments. There's no compiling, there's no uploading and waiting to see how your code changes. Now, let's see if we can break out of this code. And we're stuck in this loop. I'm going to add a if I touch the top, then turn the robot blue in this corner. And
priority.
Oh, yeah, but it doesn't work because this is a low priority. So you see priority 1, 2, and 3. You have to actually break out of the loop by inserting the code in the proper place. And there we go. Now it's blinking blue, just like I told it to. Now, if I want it to, be solid orange and go back to that boomerang, so now I'm going to send it back into priority 3. So this is what we mean by it's a touchable real interface that's not just, it's purpose-built for robots to teach the fundamentals of early coding. So I hope that explains Zach's first question of what we mean by interactive real-time coding with kids and groups. So Tony had another question around teaching kindergarten class and how can you do these activities with children 5 years in age and maybe even younger. The sidewalk activities we just showed, actually we do with kindergarten classrooms. We also do it with first grade, we also do it with second grade, but it's quite possible to do that in your class. But I think what you're getting at also is what can we do with kids that necessarily we don't want to have screen time experience. We want to have a kind of an unplugged experience. So one of the things that we've seen teachers do is take advantage of the capacitive touch, and maybe you could show me program this. There we go. So what we're going to do is we're going to create a simple program here that says on 4 rules, if I touch the top left, we're going to turn blue and take 20 steps forward. If we touch the bottom left, we're going to turn red and take 20 steps back. If we touch the bottom left or bottom right, let's turn a different color and we'll turn left and we'll turn right. So this is a program now that the Root will drive without the screen. The teacher necessarily doesn't need to have the screen with the kids, and instead, what we've seen Amy Benford do is she'll draw on the top of Root the different commands that she wants to remind herself how the robot's driving, and run the play program. And if I touch here, it goes forward. If I touch here, it goes back. Oh.
Oh, that we can do that too.
Yeah, sorry. I hit the wrong iPad button here. Root. No, Root.
There you go.
There we go. Sorry. So touch here, it goes forward. Oh man, the demo gods are not nice to us. Oh no! Actually, no.
You can actually look at his program.
My program was wrong. User error. User error. This is not intended.
He had the wrong.
Okay.
Wrong
there
button.
We go.
So he had two commands that actually both had the same trigger, and it just did the most important of them,
so
which was.
This is the nice thing with robots is that a lot of times the robot does what you tell them. It's the humans that screw up.
It's a lesson in programming there.
What's important about this, Tony, is what you can do in a kindergarten classroom is it's no longer about the coding of the robot. It becomes about the sequences of the activities you want kids to do. So like, let's say in your kindergarten classroom, you were trying to teach simple math, like, if kids were learning, 0 plus 1, 1 plus 3, 2 plus 2, 4 plus 0. And you got to call on kids to see, whose turn it is to go where they down this challenging path.
Tell Root to get to the right
and
answer.
You want Root to get to a certain area. You get to call on kids to come up with what question do they want to answer. And when you do this, the robot becomes the reward of motion. So, if Billy in the classroom wants to answer 2 + 0, then if he gets it right, he gets to tap the robot and get the robot to the right answer. So oh yeah. So what Raphael's pointing out is
I was just changing the distance so it doesn't drive quite as far.
Yeah, I drew my boards larger. So you can teach any subject with this, because you can pick history, you can pick English, you can pick your wall words, whatever you want to have the classroom participate in. This now becomes the reward for answering the correct question, but they're also learning fundamental sequencing of the operations that they need to get through. They're also, we've seen this get used with compass directions, where you have the north, south, east, west, and you have to tell the robot how to go through the different stages of a course. So that's a good fun activity, but that doesn't require an iPad, programming with the kids. But one of the special things is that, like, if you're a classroom teacher, Tony, and you came up with this code and you came up with curriculum and it just really worked for your kids, we're creating an ecosystem of apps that when you create it, you can actually name your app. And we're going to call this app RootBot. And now we have RootBot, and then you can share it on the cloud, and you can share it with others. And we're hoping that teachers out there start sharing their examples with each other, and they can share their curriculum with each other through our website as well, so that when something works for your classroom, you actually can not only share it with the world, but you can see other people's programs that worked in theirs as well. And I say classroom, I also mean homes. Like, a lot of the activities we do, I mean, even though we're using whiteboards here, Root works on paper. So, this exact example we have would work on paper just as well.
But it's a really good introduction, right? So you can start with you as the parent or as the teacher, kind of creating a set of rules on the robot and having the kids interact with it. And, then they can start to learn concepts of, like, well, what's left versus right? How would I give the instructions? Because, I mean, when you're first doing this Sidewalk game board challenge that we showed earlier, a lot of times kids have trouble, like, particularly these kindergarten age kids, of, how do I get it to move this way? I want it to go, sideways, but that's not a command. You have to learn that you have to tell the robot to turn and then move forward. And you can start introducing that in kind of a natural way where they're just, touching and playing with the robot.
So there's another question on here. We have other stuff to show, like cool robot driving games and stuff, but I'll hit the questions first. Zach wanted to know, how do we program that cool fractal image on our campaign page? We don't have a demo for it.
Yeah, so the laptop that controls. So we've been working on a couple different coding interfaces for Root. The one that we've been showing off because it's particularly special and novel is this level 1 interface that we think pretty much anyone can get started with programming with robots. But we also have been working on desktop programming interfaces in Python and Swift and JavaScript. And so our lead software developer kind of put that together just as an example of doing something with the Python API. Yeah. Unfortunately, I don't have that laptop.
We didn't bring it with us, but we programmed it 2 ways. We programmed it once on our level 3 app. We programmed it once on a computer. And the pictures you see on our campaign page are real. They're robot drawn. And
we could do another like spirally. We could do like the flower one.
Yeah. Why don't you set that up, and I'll work with another question here while you do that. So can Root draw its own game board? Well, yes, of course. Root can. I'll grab a robot to go over it. So Root can definitely draw its own game board. It has a motor here to lift and drop a marker. So when we put a marker in here, so actually Root has the ability to lift and drop it. So when it drops it, the marker sticks out just enough to draw on the whiteboard. When we lift it, it lifts it so that you can now draw whatever you prefer. So when you code a game board sequence like we've done here, you can actually create that entire game board sequence, so it'll draw the entire thing. And then if you shared that code with somebody else, they're playing the same exact game board. One of the things that is my wish for Root out there, if you're out there, you know, and excited about this as much as we are, the ability to draw your own arena is so super cool, because my kids that play in First Lego, it takes weeks of effort to build your competition arena. But the ability to then download and try a competition arena with another friend, and you have a whiteboard or a piece of paper in California and another whiteboard and piece of paper in Spain, it's the same no matter where you are. So you can actually create like games like if you had Robot Soccer, or one of my favorites is like Tron Light Cycles, where one robot's drawing and driving, another robot is finding lines and erasing them. Because one of the important parts of Root is also the ability to drop an eraser and lift an eraser. So with all that together, it's not just only game boards, it's going to be gaming activities that you can do. Do you want to show the code for that?
Yeah. So this is another example of kind of like a repetitive thing. It's not obviously the fractal image that we have as our main one, but this will draw kind of a little flower. So the commands here is when I push the play button, it's going to push down on the marker. So that's how you say, you know, if you're familiar with Logo Turtle and you have pen up, pen down, this is pen down, then it goes into one of the infinite loops that we create with our boomerangs. And all I'm doing here is actually setting two motor speeds. So I'm having the right wheel go a little bit fast, like full speed, and the left wheel go a little bit slower. And so what that ends up doing is creating a circle. And then I just do that for some amount of time. And then I turn, and then I just repeat this. And then we can, if I push play here, it's going to start pushing down the marker. I'm driving. And we'll see how this, how pretty of a picture I can make.
You want to see the execution code too?
Yeah, so it's actually highlighting what it is in the code. Obviously, a lot of times here, it's just pausing, kind of in that loop.
So it's a pretty simple program, but it makes pretty powerful results, because then what kids do is they modify the code and to create different patterns. So like instead of circles, what if I made something geometric? And what would that look like as a pattern?
Yeah, so another interesting one, yeah, you can do a loop where you just go straight and then you turn a certain angle and you get kind of these interesting star shapes and things like that. And so, it's kind of just like a creative exploration. You've got this tool that has a bunch of capabilities in the sense that it can draw and drive around, and you've got an interface so you can make a bunch of interesting rules. And I mean, it's kind of just a fun exploration in loops and fractal-like drawings where you're just doing kind of cool repetitive motions.
So why don't we show you some of the driving features of Root?
I'm almost done.
Oh, sorry.
It's all right.
Well, in the interest of time, we've been into this for 20 minutes, so
okay,
I want to keep people engaged. So let's talk about driving. So one of the things all kids love is the ability. I'm just going to load a program that's saved.
We'll use like self-driving car or something?
Yeah, we'll only just first do iPad driving. Okay. So I'm going to load a program that's saved under examples, and it's going to be Tilt Drive. So this is a simple program that says if the iPad tilts one way, so if the iPad tilts to the left, then the robot drives to the right, then the robot drives to the right. And this is the interface for setting the wheel speeds. You have wheel speed 10 on the left, wheel speed 0 on the right, which means that the robot will turn that way. And these are all touchable, so you can control exactly what the wheel speeds will be. But a simple program like this, 6 lines of code, yields one robot to connect to. So one iPad app can connect to many different robots. And I'm just cycling through which roots we have. There we go. No, I'm lost track.
There we
go. Root 5. So when I hit play, this iPad instantly becomes a controller. So, and I turn the iPad one way, the robot turns that way. If I turn all the way one way, it spins around. So kids absolutely love driving robots on walls. They also like driving robots on paper. But what's cool about this is that it's a real-time environment on a whiteboard that if we decide to change or add things, we can. But there's right now no consequences. So like if I drive over the areas that Raphael is making, oh, you're gonna make this hard on me, aren't you?
So you can't even see what I did.
If I drive over these areas, there's absolutely no consequences. So we should fix that, right? So the way we fix that is Root has a color sensor on the bottom. So this is their color sensing bar. And we go, well, if I see your choices are black, red, green, or blue. So if I see black on any of my color sensors, then we need a penalty, right? So we can, well, first maybe the robot should change its color so we know we hit it. We're going to go to a solid yellow. Then we're going to back up 10 steps. Then maybe play the music note C. Maybe make it an F. So I know that my penalty backing up is over. And then I'm going to start driving forward again. Oh, wait, but make sure, maybe I'll turn off my light. So that way my penalty is over. So now when I hit play, I have to be careful not to hit the walls, because otherwise, oh, this is just going to be too much fun. You're going to have something else. So you can. So it's not just black. Now we notice I made this as a high priority, right? So now, so it can interrupt whatever driving I'm doing. If we add a color sensor for red, we can say, well, if I see red on any of my color sensors, then I'm going to take a little baby step forward. Change that to 1. And then, of course, I should glow red because we're on it. And then that's
you
it.
can have it go forward again.
Then we'll have it go forward again. Right? So now I designed a new consequence. So now when
he reaches this kind of red end zone area, he actually is going to slow down. Oh, you have it go backwards.
Oh, I had to go backwards. Oops.
But he can change the rule in real time here. So now it goes up forward 5. So.
So this is an example of a program that we have preloaded on our app called Root Racer. And we put some fun rules in here that, like, if you go green, you go faster. So now you have your boost mode. If you see blue, that's like an oil slick and the robot spins around. But what's great about this is some kids learn by creating code. Other kids learn by modifying, and this is an acceptable way for like kids to really get creative. And then when you think about robots, and now you've created your own driving app, what about a Tesla self-driving car? Well, we can make Root a Tesla self-driving car, right?
Yeah. So we'll start. It's a little bit less fancy, but you see, you're starting to understand these concepts, and the cool thing here is we're going to do it with very, very simple rules and like very few rules even at that. So what I'm going to do is I'm going to say, all right, well, what do I want to do when I have my self-driving car? Well, I'm probably going to want to drive, so I'm just going to have it go forward. So here I just set the motor speed. I just tell the motors to drive forward, and it'll keep driving until something happens, but I have no other rules. So now I'm going to add a rule. I'm going to say if I see something on my left side, then I saw the line. So and I saw it on my left side, so I'm probably going to want to turn away from that. So what I'm going to end up doing, is I'm actually going to, well, maybe I'll have it back up a couple steps so I'm no longer on the line. I'm going to turn away from it. Doesn't really matter exactly how much because I can change it while it's running. And then I'm going to go forward. So that's kind of what I'm going to do if I see it on one side. And then if I see the line on the other side, I'll have a corresponding rule here to turn away from that line. So I saw it on my right side, so I want to turn left. And I'll go forward. So let's see how this works. Am I still on the course?
Still on the course.
So now it's going to go. Saw it on my one side.
My
So,
hands
it can kind of stay. You can see it's kind of just staying in the course. We'll see what it does when it gets to this more challenging part. It might hit the other side and turn. Oh, got lucky. So you can actually, because you have the priority system, if one of these, now it's going to err on the side of turning to the right, because this is a higher priority rule. This right turn command. So if it sees lines on both sides because it ran straight and like kind of T-boned the side of the road, then it will tend to turn right.
Awesome.
There you go. So there with what a handful of blocks, you have your first self-driving car. And this is something we've done with young kids, and they can start to understand those concepts and figure out how we build algorithms to control these kinds of devices in the world.
And as a dad of 3, a 5, 8, and 10-year-old, what's super cool is you do things that are fundamental with the robots that like still apply to what they're learning in school. Like take my 5-year-old, for example. It's cool to be able to sit down with her and talk about letter formation and then like code letter formation with her. So if her name is Bella, being able to code a B together. And it's a special kind of, selfishly, it's like a special kind of father-daughter moment where you get to like really do some cool things with robots and your kids. It's like a win-win, and they're learning something. When my kids are privileged because they get to have robots in their house, what's cool is they get to bring those robots to their classrooms too, because it's super easy to just do show and tell. So after they do something that they're proud of and they accomplish a goal, they could bring it into their classroom. They can throw a robot up on the whiteboard, and we have more teachers asking us, how can I get one too, than ever, because the teachers get it. It fits into their classroom really well. But I think the way to get there also is through the audiences, like people like you out there who are parents, getting your kids to code with Root, giving them special experiences, and then having them share those. So we've been very heavy on level 1. We just wanted to show you a sneak preview of, so level 1 right now is in a beta release. We actually have schools that downloaded this onto their own iPads and are using it in their own classrooms, K through 3rd grade. We aren't ready for a beta release yet on level 2 or 3, but I'll show you what those look like. So the goal of level 1, there we go. The goal of level 1 is really about accepting anybody. So whether you're in high school and you want to learn to code, whether you're 4 years old and you can't read and want to learn to code, we designed an interface that shouldn't feel like you're playing with a kid's toy if you're older, but it should be approachable if you're younger. So it was actually very hard to get this exact mix right, but we've taken this to high school kids and they love level 1 as much as little kids too. So the goal here is accept anybody in a graphical interface. Level 2, the goal is computational fluency. And what we mean by that is now you actually have additional conditionals that you have to read. So now you have things like when and else and loop and set and idle. And you have a framework now that's a little bit more complicated, but still graphical. And it gives you access to things like sensor values. So you see what the robot sees, and then you understand how to manipulate that information. Variables. I'm not sure if this is, sorry about the focus. I don't know how to autofocus it. Variables. This stack is a parallel stack that you can combine and run now and execute tasks in parallel. And what you're really building up is this idea of, in this interface, if you can have computational fluency, then you're ready to go to text-based coding, because you're actually creating complex relationships between sensors and variables and rules that you create. And when you convert that into text, this is now JavaScript. Sorry about, again, the horrible, there we go. This is JavaScript. And our endpoints are going to be JavaScript, Swift, or Python. We really don't care. We feel that once you know one coding language really well as a good anchor, that you can build off of that and go into new and more coding languages easier. But the concept here is now you're building off of the frameworks you've learned in level 1, 2, and 3, and we're taking you through a user experience and reusing color in a way that makes things familiar. And then when you've reached the limit of level 3, you can actually send yourself your code, and you can now go to a computer and use our SDK.
So what we really wanted was a smooth transition from I've never coded before, maybe I'm a parent or a kid, and this is brand new to me, to you are using these very common professionally used languages, and are really able to do, you know, things far beyond. I mean, obviously programming advanced things with Root or other robots, but really just true programming and full programming in the full sense of the word. I mean, you could start applying for jobs and like learning all these new other libraries as well. So what we found when we were talking to kids early on was, you know, sometimes they would play with Scratch or, you know, some other introductory languages, but first of all, you couldn't start until you were kind of late, and then once you had that, you were kind of left off, and there wasn't a nice clear path for continuing. And we wanted to be there at the beginning and lower the barrier of entry, but also have a high ceiling of what you could do. And we didn't even talk about additional like hardware things that you can add in terms of 3D printing, you know, like a backpack and adding cameras and other advanced features as well.
Yeah, so a very robot-y thing to do, I can't resist, is line following. So just to show you, again, there we go. Come on, focus camera. There we go, line following. So in really 6 or 7 lines of code, you can also make a line follower. This is an extension of what Raphael was showing before with just a self-driving car, but it can show some of the fine maneuvers that the robot can do.
Yeah, so instead of having just those 3, you know, or 2 rules, like move away from the line on each side, here we can actually use kind of the full sensor, which actually has 32 sensors, but we're breaking it up into 5 chunks. And then we can say, you know, if the chunk is only a little bit off center, maybe I just want to curve a little bit toward it and not be quite as aggressive. And so you can have a little bit of a smoother outcome from that.
So here we have Root line following our roadmap. And it's kind of cool because when you have multiple robots now on the wall, that now if you have the ability to one draw and one erase, or one line follow and one just explore the world and bump off of things, you can really get into like very creative, like almost robot art scenarios. One other sensor that we don't talk about yet, but it's on there, we haven't added the if block for, is the light sensor. So underneath Root's eyes are 2 light sensors that you can react to the lighting effects inside of the room. So if this light sensor sees bright light versus this one, versus both of them versus none, you can actually have the robot now respond to things like flashlight, and you can have kids programming robots to do flashlight tag. We also plan on adding accessories to the back of Root. There's a USB-C port in the back, and you can add things like robot-to-robot tag modules where you can, you know, send beams of information to each other, or lights so that you can follow each other, or what you saw, our Raspberry Pi camera that we plug into here, and now you can actually get vision navigation. The other fun thing to do for all those of you out there that already know how to code perhaps, these make great crosshairs for doing vision tracking. So putting Root on a whiteboard and setting up an external camera, you can cue off of this as your information, and now you have a global position of exactly where Root is. And that unleashes you to do even more things, like the activity we showed in our video was, the fun thing was we made a floor plan, and we pretended Root was a Roomba, and what are the cleaning algorithms that Root can use in order to navigate that virtual environment. Or doing some precision drawing, where we want Root to, you know, draw an arbitrary shape. Now it doesn't have to be a fractal, it can be, you know, it can be a picture that you want to program it. Another activity that I thought was fun, would be fun to do out there, is imagine like Root knew what the picture was, but you were dropping little dots of information on a wall. And so when it starts out, you just see a few dots on the wall, and then you're watching Root kind of give you more and more and more information. And at what point do you start recognizing the image that Root is creating for you? And it's another, like, you know, we're just filled with all sorts of fun, crazy ideas of things to do with Root. We don't have time to do them all because we want to get you the hardware, but we're hoping that you're going to be as excited about Root as we are. Anything else?
I don't know. Yeah.
So shoot on the chat window and typity if you have any other questions. There's 47 of you out there still, so.
And thank you also to all of our early backers.
Yeah.
You know, this is what makes these kinds of things possible. I know the Kickstarter community is just like a great place filled with a lot of people that are willing to invest in some cool and interesting new technologies. I mean, we see this as as being a really great tool. We've been working on it here at Harvard for 3 years now, and we're excited to closer to 4 now, getting older.
Seriously.
And we're very excited to finally share it and get it out into the world. I think it's really the best tool that I've seen for introducing these concepts to people really of any age.
Yeah, and when I get often asked by reporters, like, what's the thing that surprised you the most when working on Root, and I'll share that with you. When we first started working with Root, it was really with Radhika Nagpal. She teaches computer science in Harvard, and she wanted this in her classroom. But we were looking at this as saying the really hard problem to solve is how low down can we go in the learning curve, and that's why we focused on K through 5. But the thing that was surprising to me the most is when you look at kids and coding, we started designing this for K through 5, but really it's really all kids that really want to have access to level 1. It's not like level 1 is your kindergarten, your 4-year-old to your 9-year-old language. It was really surprising when we were going into high school and seeing how few kids actually take computer programming. And all the kids that don't, how instantly they fall in love with Root and they want to say, I want to use this too. And it really made us spend an extra time when we learned this to make sure that we had an interface that worked for them. So it was, not just solving the K through 5 robotics problem and coding problem and then this other stuff, but really how can we holistically do everything together? And what we're hoping to accomplish now is that we're going to have more kids caring about coding and understanding how digital stuff really works. It doesn't necessarily mean, if you're out there, that we think all people should be computer scientists, because we don't. But we think it's just a fundamental thing that people should just know, and we think it's critically important for the future of everyone to actually know that it's not just being a consumer of information, but it's actually being appreciative of how things work. Kind of similar to, we all take or dissect frogs in class, and we all learn about anatomy, but we're not all going to become doctors. But it gives us a new appreciation for how that world works as well. And when you think about the older kids, yes, Root can fit there and it's great, but we don't want to wait until kids develop their interests and then get offered computer science as an elective in high school. The first time I got to take computer science was in college. So, in this generation, I think it's kind of laughable that most kids don't get exposed to computer science until high school. And we think that this is also going to be a fundamental tool so that if your kids are young right now, that this can be something that gives them the opportunity to develop an interest and keep that interest and grow with that interest as they grow up. So, sorry about, the long monologue there, but I guess we're just going to wrap it up unless we get another question. So I'll give you the few minutes.
But to your last point, we see this as kind of a nice investment in learning computer science, particularly for your kids or in schools, because it does scale well, and particularly for schools as their other technologies, like maybe they get some new laptops or new iPads or things, you just still use those new things with Root, that it will have a much longer lifetime than a lot of these other tools out there.
I feel like we have to have one of those, but wait, there's more activities. Order now and get, whatever.
No, we're not good enough for home shopping network yet.
But for 3 low payments of $49.95. So help us reach our goals. That's, if there's one thing, if you're excited about this demo, really get the word out there, because it's going to be extremely important. Oh, we got a question. Yeah. That's from Todd. How do you think older students will remain engaged? You mentioned something about add-ons in the Kickstarter video. Care to share more? I will share that question with the audience. There we go.
Yeah, so I mean, we touched on a couple of these other concepts in the sense of you can do really advanced things. I mean, Radhika Nagpal, the computer science professor at Harvard, wants to use these in her class, and you can do really true advanced robotics things with this. Either connecting a camera like a Raspberry Pi camera or something similar, and doing those advanced computational things, or just if you have external tracking, you can control multiple roots from your laptop, say, do some advanced foraging behaviors or advanced drawing, or we talked about the Roomba algorithms and things like that. So there's a lot of
maze solving. You can have an arbitrary maze put up on the board. Everybody has to code a solution to it, and then you're actually watching each other's solutions unfold, and then you're actually seeing people's code, perform against other people's.
Something else we'd like to do is ultimately, when there's a lot of roots out there in the world, is create some sort of competitions and things where people can. I mean, it's great because the roots can draw their own courses, and so they can create some challenge, and then roots can compete against each other. And when you have that level of multiple roots kind of interacting with the environment that they're changing, you can. Being able to solve that problem is incredibly difficult, and so. The limits of this are really quite high. And on the hardware side, you'll be able to add your own accessories and things as well. So schools have started getting these 3D printers, and we have actually really started on Thingiverse some designs for a backpack that can you can edit and put whatever you want on there. But we started with one that you can screw in a Raspberry Pi module. So.
Yeah. So I think Root can intersect the kind of the maker phenomenon. And I think what Raphael is getting to is that it's really not, what experience Root can give you, but what experience you want to make Root get. It's not really what experience you have with Root, but what experience you want to make with Root. An evil thing to do, I just thought of while Raphael was talking, is we spent 4 years working on this, not because we needed to figure out how to add wheels on here, but it's actually really hard drawing on walls, and we can actually disable everything that we've done, and then it's a college level problem to figure out how to get this to drive accurately on whiteboard walls. So that would be, there's things that we make sure that Root just works out of the box, that the encoders that you have behind these wheels, so that when you tell the robot to go straight, how does the robot know what straight is? Or if you tell the robot to turn, how does it really know if it turned 90 degrees versus 85 degrees? These are all things that are happening under the hood, and it's actually using a gyro, an accelerometer, wheel encoders. It's using the magnetism of the whiteboard as feedback. And we have a lot of parameters embedded in a Root for it to just be working robustly. Because in level 2 and level 3, you have access to the raw sensor values, you now have an opportunity to actually fully understand what's actually going on behind the scenes and why we actually made the decisions we made. And it's just a cool thing. And, it's more about having the ability to, in a physical world, understand those complex things than it is, trying to force kids down one particular path. Because when you do learn computer science and programming out there, it's not that much fun. It's kind of pretty lame, to be honest.
It can be fun.
No,
the act of coding is not always the most fun, but it's rewarding to create new things. And we found that doing it with robots makes it fun from the get-go for starters, because you're kind of doing some new and interesting things. And with the right interfaces and the right library, you can get to the point of doing these interesting things much faster. So our goal when we've been working on this project from the beginning was to remove a lot of these frustrations from learning how to program and learning about computer science.
Cool. Excellent.
Cool.
So
share with your friends.
Yeah, exactly.
We still have, I think, halfway to go. So if you know anyone else who would be
and we're just so
interested,
honored to have in 10 days go as far and fast as we have with you guys. And we're just looking forward to hitting our funding goal and beyond to get this to you as fast as possible. So heartfelt thanks to everybody out there that backed us. Hopefully this helped those of you who haven't, help you bridge that gap. And we'll stay tuned. We're going to do another one of these Kickstarter lives next week. We'll post it on our campaign page. We'll also send some tweets out about it. So in case one of your friends missed this, just keep an eye out for that. And we'll send another update later this week. So thank you, everybody, and take care. Thanks for watching. Go to codewithroot.com if you want to find out more. How's that? All right, awesome, everybody.
Thanks so much.
Thank you. And